Hello, everyone. Very happy to see you all here. Welcome to the M53 sharing session. So, if you like what we are doing, so basically we are doing this sharing almost every 2 weeks. So on Tuesday night, if you like this, remember to follow our Twitter and then subscribe and don't miss out our content. So let's start this. So a bit about myself. I'm Kelsin and my Discord name is MacFrogHead8. And I usually play for several CTF teams, including M53, NUS Grey Hats, and iMonkey Pro Max. For iMonkey Pro Max, I only use it for local CTF. So if you see the local CTF team with iMonkey Pro Max, I probably will be inside unless there are some imposter. So I'm currently a student still studying in NUS for computer science and math. And I will be joining the PhD program for in NUS soon. And I will do cryptography research. So for this whole thing, right, there are a lot of things to cover actually. And I will start by talking about motivation for 5 minutes. And then math background. So this would take approximately for 2 hours. It will be a very heavy content on abstract algebra. Actually not very heavy, but there's just a lot of things to cover. And then the equation solving part is only at the very end, and it should take about 30 minutes. So there really isn't a lot of techniques to learn here, but so why do we need this abstract algebra background? Is because we need to understand how the tools work. So without this abstract algebra background, even if I tell you how to use it, you probably won't adapt it to on different scenarios. So because we can't like just put in all the contents for so long, right? So we split it into 2 parts, and then we'll continue the second part next week on Tuesday at the same time. Okay, so yeah. So let's start. So why do we even care about equations? Firstly, maybe this is the most motivating thing for you all is you all play CTF. So if you all play CTF, you know that CTF Crypto Challenge, they like to have all sort of equations problem. So like for example, we can see from this Python code snippet, the flag is encrypted, not encrypted, it's converted into numbers. So X is the flag. And then we initialize elliptic curve. If you don't know what this is, it's fine. But so yeah, basically we initialize the elliptic curve, and then we assert these 2 statements, and then that's all. We print out all of them. So this actually takes less than 20 lines of Python code. And to solve for the flag, right, you just need to solve for this X. And how do you solve for this X? The only hint that you have is these 2 assert statements. So these 2 assert statements actually correspond to these 2 equations. So in other words, if you can solve these 2 equations, then you can get a flag. And in fact, this was a question in ACSC 2031. And this question actually, I remember there was only like 3 to 4 solve for this question. But the solution for this problem itself only takes like 3 to 4 lines. So so it's actually very simple to solve. That's what I'm trying to say. But the thing is, a lot of people, they don't know like the techniques there. So if you don't know the techniques, then you feel that this is very difficult. But if you know the tools and the techniques that you can use, this will be a very simple question. So this is the reason why for crypto CTF questions, right, you can speed run all of them. If you know it, then you know how to solve. If you don't know it, then take you a week, you probably still cannot solve it. So apart from the CTF motivation, another reason that we care so much about equation is cryptography heavily relies on mathematics. And we have different primitives out there. We have RSA, we have elliptic curve, we have discrete logarithm, we have AES, Xbox. All of these have some sort of equations inside. And so to understand the equation itself is necessary for you to know how the crypto works. And perhaps last reason on the motivation part is on post-quantum crypto. So not sure if you all have been following the news, but quantum computing has recently been there are a lot of things going on with quantum computing. And then the biggest thing that they can solve now is that they intend to solve is the computational Diffie-Hellman problem and integer factoring. So for these two problems, they can we have quantum algorithm to solve it in polynomial time. So if we can construct a good quantum computing quantum computer, then we can solve these two problems. So this is actually a very big issue. Why? Because most of our crypto system relies on these two problems. So if these two things can be solved very quickly, then our crypto system will, in a sense, be broken. And that's why there have been a lot of research work going on to try and find post-quantum cryptography. So this post-quantum cryptography basically means that we want to find schemes that are resistant to quantum algorithm, schemes that cannot be broken by quantum algorithm. So it's very hard. It's not easy. But so people have been trying to do this, and there have been many different constructions that people have proposed. So the first one is the lattice-based approach. If you know, then it's fine. But if you don't know, it's also you can just ignore it. Then for the code-based construction, this is based on coding theory. So the coding theory here is different from the Python code that we do. This is on channel coding, so like communication coding. And then there's also the hash-based construction, multivariate construction, and isogeny. So I'll talk about multivariate and isogeny in a bit. So for multivariate construction, right, it relies on hardness of solving system of multivariate polynomial equation in finite field. There's a lot of jargons here. What is finite field? What is multivariate polynomial equation? But basically, multivariate, just you need to solve equations, and then the hardness of the construction of this whole thing relies on this part itself. And then for isogeny, it is constructed based on elliptic curve group, and then it is quite complicated, but ultimately it relies on group homomorphism. So why do I talk about these two specifically? Is because for multivariate scheme, we have this rainbow. So this scheme is called rainbow, and then it is a public signature scheme. It is introduced in 2005, and it made it to the competition, to the round 3. So the next round started in 2016, and then this made it into round 3. I believe round 3 was around like 2020 or something. But what happened in the end is that it is broken in 2012. So a lot of people thought that it was secure, and indeed at that time it was secure. But then just one paper itself in 2022 show up and show that they have an attack on the signature scheme. And basically all the work that has been done on this before has all been just gone. Then for isogeny case, we have this scheme. So this is also a signature scheme. And then again, it's introduced in 2011, made it into round 3 and round 4, but in the end, it was still broken in 2022. So there have been a lot of optimization and implementation for all this algorithm. But now it has all just become a CTF question. Because so like imagine like you implemented the C algorithm for this, you do it in a lot of different programming languages, and then you do a lot of libraries for all these schemes, but then in the end it's just your effort just gone. So it's very sad. So that's why it is still very much interesting to look at crypto system itself. So there are still a lot of works that can be done. So for researcher, this is very good. So we still have job. So ultimately, what we are trying to say is understanding equation solving. Let us know what is hard and what is not hard. So perhaps we can don't make the same mistake that multivariate the rainbow scheme did. And then it is also essential to create protocols and primitives that are secure. So this will be the motivation part. And any questions? Okay, in that case, then I will move on to the math background. Okay, so yeah, so here I will start to talk about groups. And then furthermore, I will talk about rings and if we have time, then we can talk about fields. You might have seen you might have seen all these jargons before, but here I'll introduce it to you. So first, we have to start everything with counting. So imagine now we have a monkey. Okay, so this monkey is a monkey, and the monkey likes to eat banana. So here's a banana. So monkey likes to eat banana. So monkey collects banana. So when monkeys collect banana, monkey put everything in a box. So there are a lot of bananas. So now monkey wants to know how many bananas are there. So monkey needs to perform counting. So for counting, here we derive our integers. So more specifically, our positive integers, which is basically representing how many things are there. So like for example, 1 is just 1 banana, 2 is just 2 bananas. Then now the monkey has a box of banana, but monkey will eat the banana, right? So when monkey eats the banana, the banana will, okay, actually before that, I just want to mention that this set of numbers, right? If we put it together, it is called a natural number, and then we represent it with n. So this is the natural number. So back to what we said just now. So monkey will eat banana, and then for some banana, maybe it's spoiled, and then monkey throw it away. So now in the end, we have no bananas. So from here, we can derive the opposite of counting. So the opposite of it would be our negative number, which is -1, -2, and so on. And then for this negative number, we combine this with the notion of nothing. So we call the 0 nothing. And then we combine it with our natural number, which is for our part. So yeah, I think I should also mention a bit of set theory here. So this notation here means that you put this thing and this thing together. So basically, you just combine these two stuff together. So with that, you get the set of integers. So for this set of integers, so another way of writing this is that so basically this is just like you combine these two things together, right? Similarly for this. So you can also write it as this way. So you just so here is that it is continue to -3, -4, and so on until -infinity, and then here you continue to positive infinity. So this integer will be the simplest group that we will be looking at. So now we have to define what is a group, and so first let's talk about binary operations. So imagine we have this binary operations slash, I call this slash, on the integer set z. Then I ask you, what is 1/2? Well, perhaps you can't answer this question because I haven't defined what a slash is. So here, let me formally define what a slash is. So a slash is basically, the slash will take in 2 integers. So here, the 1 is basically the integer here, and then the 2 is the integer here. And then the result will also be an integer. So this is just a fancier way to write down to define the operation. So we actually, in math, we call this like domain, if you remember. And then this is the codomain from your SPM. So now what happens is that I can define my binary operation slash with anything I want. So for example, I can define my binary operation A/B to become A plus B. So what this essentially means is that 1/2 is just 3. 3/5 is just 8. And then -3/3 will be 0. So essentially what we are doing here is that we are sort of make this addition into a variable. So we don't explicitly say out what we are trying to do. So we are making, it's like you putting x. So in math for SPM, right? So you put x to represent unknowns, right? So for here, you are doing this similarly, but you put slash to represent unknown operations. So is this clear? Yeah, okay, good. Okay, so now we have a binary operation, and let's say we have a set of elements. So a set of elements is just a collection of stuff. So we can think of it as a box, and then a box will have a different things. So like for example, for integer z, it will be a box, and then this box we have -1, -2, 0, 1, and so on. So it's just a collection of things. It doesn't really mean anything. So it means a lot of things, but it's a collection of things. So the first property that the group must satisfy is a closure property. So what is a closure property? I pick any two elements A, B from the set S. Then if I do A/B, I must also be in the set. So this notation here basically means that A/B must be inside the set S. So this is the notation of something is inside here. So it means that if this is my set S, then there will be some A/B here. There will be some element A/B here. So intuitively, you can just think of it. If you think of this as an integer, so if the set of integer is, so let's say if my S is the set of integer, right? Then if I add any two integer, I add A plus B, this will become another integer C, and C will still be an integer. So this is the closure property that for a group. So for the second property that we need to have is associativity. So what do we mean by associativity? We pick any three elements A, B, C from the set S. We do slash on A, B first, then only afterwards we do on C, or we do A/B/C. So we do this part first, or we do this part first. The result should still be the same. So if you think of it from integer point of view, it basically means that 1 plus 2 plus 3 is equals to 1 plus 2 plus 3. So no matter you do this part first or you do this part first, it doesn't matter. So clearly this holds for addition, right? In integer. But so now I would like to have some interaction. So can you all think of any binary operations that does not satisfy associativity? Basically a counterexample. So so any binary operations that we have learned before, division. So division is a very simple example. So like for example, 1 divide by 2. Okay, 1 divide 2 divide 3. If you're doing 1 divide by 2 first, and then you divide this whole thing by 3, then you will get something like 3/2. And then if you do the other way around, which is 1 divide by 2 divide by 3. Actually, this is not a very good example. Let me do it again. That's 3 and 4. 3 divide by 4 and divide by 5. If I do this part first, this will be 3 divided by 4. And then this whole part will multiply with the reciprocal of this. So this will be 3/20. And then if we do the other part first, which is 4 divided by 5, this will become 3 multiplied with, okay, so I should do, 4 divided by 5 is this. And then I move this part up, this will become 3 multiplied by 5 divided by 4. So it's not the same. Okay, so it's not associative. Division is a very good example. Another example that we have is negation. So for example, 1 minus 2 is -1. -1 minus 3 is -4. 1 minus 2 -3, this is 1. And then this is -1. So 1 minus -1 will be 2. So negation also does not satisfy associativity. So it is not always true that any binary operations that you have will satisfy this thing. So usually we still have to do some checking on whether the operation satisfies associativity. Now, the next thing that we have is identity element. So for identity element, we basically say that there exists an element E such that for any element A in S, E/with A will be equals to A. So here I didn't mention one thing, but this element should be unique. Means that there is only one element that can satisfy this property in the whole set. So in the integer example, 0 will be this special element. So because 0 plus a will be equals to a, that is obvious. But for division, this might not be that true, right? Because 0 divided by a is, okay, 0 divided by a is definitely not a. And then, so we still have to find this element. And then the last one is the inverse. So for any element A, there exists another element B such that A slash with B will be equals to the identity element E. So sometimes we also call this element B as A inverse or negative A. Again, for integer, for the set of integer, the negation of 2 would be negative 2. So for every integer A, you can always find a negative counterpart such that this will become 0. Yeah, so if I write this in A, this will be A plus negative A, minus A will be 0. Okay. So with all these 4 properties together, we call this thing a group. Okay. Yeah. So we call S. So we say that this is a group. So we just tuple it together. We put S and the binary operation together, and then we put the G. So we call this a group. So when I say a group is something that satisfies all these 4 properties. So yeah. And then the question is, do we require this property? Yeah, from the chat, division doesn't even satisfy closure property. Yeah, so division has a lot of problem. So okay, so for this, right, this is not explicitly stated, but so later on we'll see that a group does not necessarily have to satisfy this. But in the case of integer with addition, you will see that this is very obvious. 1 plus 2 is equals to 2 plus 1. You can always change the position of it. So, but it's not necessarily the case. We'll see example on that. Okay, so let's start with some quizzes. Okay, is this a group? So this is a integer with the operation addition. Okay, let me start a quiz. Okay, is this a group? I have started a poll. Not sure if you all can see. Okay, I see votes coming in. Yeah, so okay. Although majority of you all say that it is a group, there are a portion that says that this is not a group. So perhaps let's just try and prove whether this is a group or not. So we take any two integer a, b from the set. We check whether it satisfies closure. So again, a plus b will become c, right? So this is an integer. This is an integer. An integer and add with an integer will still become integer. So it satisfies closure property. Does it has an identity? Yes, it has, because we can always add 0, right? So 0 is an element from that. We can 0 plus a is always equals to a. So identity is satisfied. What about inverse? We have the for every integer, we have the negation of the integer. So a plus negative a, this will become 0. So inverse is also satisfied. And associativity, this is also true, which we see just now. A plus b, if you do a plus b first, or if you do a plus b plus c first, this will all still be the same thing. So this is a group, and we can check that all the properties are satisfied. Perhaps a not so trivial example, would this be a group? Okay, so let me end the previous poll and start a new one. So this is the operation multiplication on the integer set. So is this a group or not? Remember that we are just replacing this slash with multiplication. And we know how multiplication is defined. Okay, I'll give 10 seconds. Okay, 11 votes says that it is not a group. 8 votes says that it is a group. So, okay, let's check. So first, closure property. For any integer a, if I multiply with another integer b, this will still become an integer c, right? Because if you see like 2 multiplied with 3, this will become 6. Although it's kind of hard to actually justify this fact, to prove this fact, but we know that this is true. So closure is satisfied. Does it have an identity? Yes, it has, right? Because 1 multiplied with a, this will become a, and then so 1 is our e here, and then a, yeah. So we have an identity 1. So this is satisfied. Okay, then what about associativity? So a multiplied by b, if I do the front part first versus I do the back part first, would this be the same? It is, right? Because 2 multiplied by 3 multiplied by 5, if you do this first versus if you do like the back part first, it will all still be the same. So okay, so these 3 properties are satisfied. So now let's check what is the inverse. So okay, I'm asking, okay, so let's just take an element 2. Is that an integer a? Okay, that when I multiply 2 with a, this will become 1. We will see that, okay, a in our case, right, is 0.5. Or we can write it as 1 over 2. So 0.5 and 1 over 2 is actually not an integer. So this is a rational number. This is not an integer. We cannot say that there are 0.5 in our counting, right? The things that we say just now, we don't have the notion of half yet. So 0.5 is not an element in the integer set. So that's why the inverse property is not satisfied. So when the inverse property is not satisfied, this is not a group. So now another question is, what elements here have inverse? So we know that 1 definitely has inverse because 1 multiplied by 1 will be equal to 1. So remember that our identity in here, our E in this group is equal to 1. And another integer that has inverse is negative 1. So negative 1 multiplied with negative 1 will also be 1. So there are only 2 elements here that has inverse, which is 1 and negative 1. Okay, hope you are following so far. Okay, so now let's look at this element. Okay, so what is Q? Q is the set of rational number. Q is all P divided by Q, where P and Q are integers. So Q is the set of rational number. So your 1 over 2, your 1 over 2, oh wait, mine. Okay, yeah. Your 1 over 2, your 1 over 3, your 4 over 5, you name it, it's all inside Q. So is this a group or not? Okay, let me create a new poll. Is it a group? So we sort of fix the problem of not having an inverse, right? Just now we say that inverse of 2 doesn't exist. So in Q, we force it to Q inverse of 2 exists in Q. So what? So is there any other problem, or this is indeed a group? Okay, give 10 seconds. So there are 8 against and 8 uh supporting. Okay, now it's 9-9. Okay, very interesting. Okay, so half of y'all say that it is a group, half of y'all say that it's not a group. I would like to ask those who say that it is not a group, why is it not a group? If it's not a group, why is it not a group? Since you mentioned, you said that it's not a group. Can anyone just type out the reason that it is not a group? Yeah, so David say correctly. The problem here is 0 does not have an inverse. So it looks very nice, right? Okay, everything has, okay, 1 has an inverse, 2 has an inverse, 1/2, we have everything inside. But we remember that there is another element here, which is called 0. So this 0 element does not have an inverse. We don't have any element. Oh, my mouse is acting very weird. Okay, so yeah, we do not have anything that multiply with 0 is equals to 1. And if you try try to divide this thing, you get like 1 divided by 0, and we know that this is undefined. So actually there are no inverse for the 0 element. So this is not a group. Okay, so now I remove the element 0 inside. Is this finally a group? Let me make another poll. So is this finally a group if I remove the element 0? Okay, words are coming in. Yeah, so I guess majority of you all say that it is a group, and indeed it is. So every properties are satisfied. So we finally get our group. So here we kind of see that um, it is not always easy to just form subgroup, right? You still have to satisfy all these 4 properties, and then these properties is not just given. Is that you still have to work towards it. You cannot just like put out some sets and some operations and hope that it can become a group. So next, let's look at this. Perhaps I will skip this part. So I'll skip the poll for this part. So this is clearly not a group because firstly we don't have the 0 here, and this is addition. We don't have anything that when you add it together, it becomes something inside. And then there are also the problem that we don't have inverses. So yeah, there are a lot of problems here. So the next one is this. Okay, so this is 2 times 2 matrix, and where the first element is integer, the second element is so the first 3 elements are integer, and the last element is a rational number. So remember how matrix matrix addition works. So if you have A, B, C, D plus E, D, E, E, D, F, G, then this will give you A plus E, B plus D, C plus F, and then D plus G. So you just add every element one by one. So now again, is this a group? Okay, so we have 9 votes saying that it is a group and 6 votes saying that it is not a group. For those that say that it is not a group, can you all point out the problem here? Maybe type it in the chat. Is there a way to quickly identify whether a group it is a group or not? Well, you have to check all the 4 properties. That's the there is some techniques. So some technique involve like you just take any element and then you try and do something like A, B, C, D minus E, F, G, H, and then you check whether this thing is inside, whether this thing is still inside here. So if this thing is still inside here, then it is a group. But so if we try and okay, so this is very math, right? This is actually one of like if you study math, right? Then you might encounter this kind of problem in exam. And then if you want to prove so the exam questions might just give you tell you whether this is a group or not. And so sometimes we just write down all the axioms and prove it. Yeah, but so the poll result shows that 9 says that it is a group and 7 says that it's not a group. But actually, this is a group. So the reason being that every element in the matrix is independent with each other when you do addition. So it will not interfere with each other. So if you take like 1, 1, 1, and 0.5, you add with something else like 0, 1, 2, and then 0.3, you will still get something here. You still get something from this set. So the first 3 elements are still integer, and then the last element could be a rational number, but because element wise it is independent, so it doesn't affect anything. Okay, so now what about this? So this only have 2 elements, -1 and 1, and then it is doing the multiplication. So now is this a group? Sorry if this is getting a little bit repetitive. I hope it's not, but I guess it's still kind of important for you all to get the basics right. Okay. What happened to my mouse? Okay, let me launch the poll. It's okay. Okay, it seems like a huge majority of you all is saying that it is a group. There is still a minor fraction that says that it is not a group. So yeah, so let's just do a basic check, right? We take 1. So closure property, we only have 2 elements, right? So this can only be 1 or -1. So 1, if multiply by 1, this will surely be 1, and this will be inside. And 1 multiplied with -1, this will be -1. -1 multiplied with -1 will be 1. -1 multiplied with 1 will be multiplied with 1 will be 1. It will be -1. Sorry. Okay. Yeah. So closure property is satisfied, and then you can check that identity. There is an identity element which is 1. Inverse is also satisfied because the inverse of -1 is -1. And then associativity holds because these are all integers. So yeah, so this is still a group. And notice that this group only have 2 elements compared to all the examples that we gave just previously, which the group size is which we have like infinite group size. So there are infinite elements here, but for here we only have 2 elements. So okay, so I think this is the final few examples. So I'll just skip the poll for this one. Whether this is a group or not. So you can check. This is actually called a group of even integers, because if you add any 2 integers together, then it will still become an integers, and then yeah, so every property is satisfied. What about group of odd numbers? If you do group of odd numbers, certainly you will not be satisfied, because 1 plus 1 is equals to 2, and 2 is an even number, and it's not inside the group of odd numbers. Okay, so the set of odd numbers is not a group. So, but it's clear that even integers is a group. Okay, so now this is the more interesting one. I'll create a poll for this. Okay, so basically what this is saying is, this is all the elements that I replace A with an integer, I replace B with an integer. So for example, 1 plus square root of 2 is inside here. 7 plus 5 square root of 2 is also inside this set. So this is a set of collection of all of just like 2 plus 2 square root of 2 and anything like. Basically, you just like the first part and the second part is integer. So whether this is a group or not. Okay, 10 more seconds. Yeah. So 7 of y'all say that it's group, 2 of y'all say that it's not a group. So we can check. I guess associativity is obvious, because addition, and then this is, if we think of it as real number, so this should be obvious. Inverse element wise, A plus, suppose we have A plus B negative 2, we can always take another element which is negative A, negative B, negative 2. So this will become 0, and 0 is our identity element. So 0 plus A plus B square root of 2. So this whole thing, 0 is here indeed, because we can replace B with 0 and then A with 0. So 0 plus 0, this whole thing will be 0. So this will still be the original element. And then maybe closure is not that obvious, but let's just check for closure. Suppose we have A plus B square root of 2 plus C plus D square root of 2. Then I can combine the first 2 parts together, so I get A plus C plus square root of 2. I factor it out, and then I get B plus D. So this part is still an integer, and this part is still an integer. So the closure property still holds. So because of that, yeah, so this is a group, and we actually have a name for this. It's called a group of quadratic integers. Square root of 2 is kind of arbitrary, but you can replace square root of 2 with square root of D, where D is any number that is square free. So basically like 3, 5. You can't put 4 because 4 is 2 to the power of 2. Yeah. So this is called the group of quadratic integers. Okay, so far until now, any questions before I move on to the next part? Okay, yeah. So the next part, yeah. Okay, actually, I can continue with this first. Yeah, never mind. Let's just continue with this first. Okay, so this example is okay. So what is this operation? Okay, we represent the circle here as just put element inside. So like for example, okay, so let's say if I say this is the slash operation, so A slash B will be equals to A plus B plus C plus 3. So I just put this A into this first circle, B into the second circle. It's a kind of a fancy correlation, a fancy way to say that you just put things inside. But if I put circle, it means that I have to fill out something with it. And then A slash B will be A plus B plus 3. So now this is a rather harder question to see whether this is a group or not. You can think about it yourself, but I will just walk through the solution. Okay, so first, again, closure is obvious, right? Because you can just take any two element, A plus B. Okay, so A slash B. A slash B will be equal to A plus B plus 3, and this will still be an integer. So closure is obvious. What about associativity? So we write it out explicitly, right? A slash B will A slash B slash C. If we do the front part first, then we get that A plus B plus 3 first, and then we treat this as an element, and then we put this part inside, and we put this part inside, these two parts inside. Then we get A plus B plus C plus 6. So the other direction is still the same thing. So you put it as two elements, and then you put this part here and that part here, and then you get that this is the case. So we get that this is associative. So do we have an identity? So to check identity, maybe we don't know what is our identity. So we let our identity to be E. And then we know that identity, when we do identity slash with identity, we should always get back the identity. So we just check, okay, if this is the case, then I can put identity, so I just express this first part to here. So after expressing into here, then I get that E plus 3 is equals to E. Then I get my identity is negative 3. Okay, this could look a little bit weird to, but so yeah, but it holds, right? So if I sub in negative 3 here, negative 3, then what I get in the end is negative 3. So which is our identity. So our identity here is not 0, but it's negative 3. It might not be that intuitive at first, but I kind of like force it to be negative 3 because of this operation. So the last one that we look at is whether it has inverse. So if we want to check whether something has inverse, then we take A and then we take B. We suppose that exists an element B such that A when I do the things with B, then I'll get E. Then I just expand this out, and then I get A plus B plus 3 is this. Then I get my B is negative 6 plus A. So this means that A slash with negative 6 negative A will be equals to the identity. So the identity in our case is negative 3. Although it seems a little bit artificial, but this is a group, right? Because it satisfies all the 4 properties. Okay. Yeah. So yeah, before I move on to why do we even care about doing all these things, right? Any questions so far on how to do the identifications and some, yeah, any burning questions? Okay, seems like everyone is fine. So hopefully, yeah, hopefully it's okay so far. But if you have anything, just ask in the chat. I'll get the chat periodically. Okay, so now we go back to the most important question on why do we even care about doing all these things? We prove that something is a group, but why? So okay, the most important thing about group is the shared property. So because we define our group based on the 4 basic properties that we have, if some properties exist for a group, that means that all collections that is a group will still have the same property. So for example, in the group of integer with addition, we can solve this kind of equation, right? So let's say my x is an unknown. We can always, because we know that 1 has an inverse, so we can add with the inverse on both sides, and then we get that x plus 0. So this is the inverse axiom, not the axiom, the properties. And then x plus 0 is x. This is the identity property. Then we get that x is equals to 2. So in the group of integer with addition, we can solve the equation similar to this. But what if I just change this to something else? Like I change this to x multiplied with -1 is equals to 1. So again, I can completely do the same thing and get a result. So what is good about this is that if we have an algorithm that can solve that type of equation in a group, then we can solve it in every group. So we don't have to repeatedly define our algorithm for different groups and so on. So this is very good. So this is the reason that we actually care about doing all these things. So group is essentially it's just a collection. We are just classifying things such that they have the same property. So now I say that if I have an algorithm that I can solve for this group, then we can solve it for every group. So that's very nice. So now let's just look at a concrete example on how do we solve equations and group, and let's try and design an algorithm to solve it. So for example, if we have a group, right, and then we write it as so we want to solve this type of equation. Actually, this is a very general equation because if we have like A1, suppose we have a lot of different items before here, right? Before A, we can always combine it together and get A. So I just simplify it as, so this A could be A1 cross with A2 slash with A slash until AN. And then B, similarly, B can be something else, but you can just combine everything together. And we see that this is easy to solve. Why? Because of the group property. So we have the inverse element for A, we have the inverse element for B. So we can always take the inverse on both sides, and then we get that this, and then we can solve for X. So it's easy to solve if we are dealing with a single variable with degree 1. So what about multi-variable with degree 1? So suppose we have A slash X is slash B is equals to C slash Y, and then similarly for D slash X slash E is equals to F slash Y. Okay, that's very mouthful. But so we show that actually this is also quite easy. Why? Because you can always express X in terms of Y and do substitution. So perhaps a more concrete way to write it down is that you can do something like if you have A cross X cross B is equals to C cross Y, right? Then you just move everything to one side, so you get that A inverse cross C cross Y slash I should say slash instead of cross, yeah, slash negative B. Then we express X in terms of Y. Then we put this back inside here. Then we get a single variable degree 1 equation. So this will be something with Y, and combine it together. Then the whole thing will be easy to solve. Okay, so yeah, so we can see that solving equation in group is with degree 1, even for single variable or multi-variable is easy. So what about high degree? If I do it for n times, and then I want you to solve for this equation, is it easy or hard in the group? Perhaps let you all think about it for a few seconds. And if you have any thoughts, maybe you can just put in the chat as well. Is it easy or hard? Okay, two of you all say that it is easy. David says that it feels hard. What about the others? Do you have any thoughts on this? Any feelings, intuition on whether this is easy or hard? Yeah, so basically we are solving like X, you combine, so you have so you are this x is unknown, right? And then you are doing it a lot of times, n times, and then you get that this is equals to a. So yeah, okay. Maybe some of you will think that it's easy, some of you will think that it's hard. So let's see some examples. Okay, so for example, if this is addition, right? If this is addition, then x plus something plus x then equals to a. Then what is this? This is nx is equals to a. So we can divide n on that side to get that a divided by n. My mouse. Okay, a divided by n. Yeah. So in the case of integers, with addition, this is actually pretty easy because you can just do division. But then, if you know RSA, the security of RSA actually depends on this itself, right? So for RSA, we are raising some numbers to e times. So we are doing m to the power of e. So we are doing m to the power of e, congruent to c mod n. And then if you say that this is easy, then we can break RSA already because we can always find the m, right? So basically, it seems that for some of the groups it is easy, but for some of the groups it is hard. So that kind of demotivating a bit because we were saying that okay, if you can solve something in the group, then we can solve it in everything. But seems that with just the group property itself, it might not always be the case that this is true. So yeah. Okay, so yeah, perhaps now I'll also talk about a non-commutative group. So when we say that non-commutative group is basically when that A slash with B is not equals to B slash with A. So matrix is a very good example of this. For example, if you do something like 1, 1, 2, 0, you multiply this with 2, 1, 0, 2, 1, 1, 0. And then if you do it the other direction, you might probably get the other things. But okay, I believe you should know this from SPM mathematics. So I will not refer to this. But basically, if you do A multiply with matrix B, it's not always equals to B multiplied with A. So this is not always true. And then the question whether this is a group or not, just now I have shown an answer. This is not a group because we don't have an inverse inside. 0, 0, 0 does not have an inverse. So what is the identity here? So the identity here is exactly this. So if you remember that for any matrix, if you do 1, 0, 0, 1, you multiply with any other matrix, you'll get back the matrix A. So we have an identity. So how do we make this in a group? So there are many elements here that does not have an inverse. Like for example, if I just even though I just put like I know that 0, 0, 0, 0 does not have an inverse, but 0, 1, 0, 0 also does not have an inverse. So there are no elements A such that this multiplied together would become 1, 0, 0, 1. So regarding why this is true, I guess it's kind of hard to prove direct. Yeah, it's kind of hard to prove as directly now, but basically I think you should kind of know that yeah, so not every time that we have the inverse. So we have to check whether this has an inverse or not. And then if you remember that we have when we have A, B, C, D, when we want to check whether this has inverse, we have to check the determinant of this, whether the determinant of A, B, C, D has inverse. And then the determinant is A, B, C, D. We write it like that. And then this is A, D times minus with BC. And then if AD minus BC is not equals to 0, then this has inverse. I hope you still remember something like that. Or this may recall some of your nightmares. But yeah, so matrix only have inverse when AD minus BC is not equals to 0. So how do we make this in a group? actually we can do something like this. So we remove all the elements that does not have an inverse. So basically what I'm saying here is I include all the elements A, B, C, D, and I only include the elements that the determinant. So this is the determinant notion, or equivalently, this is equals to AD minus BC. And then so if AD minus BC is not equals to 0, then I put it in the set and then I do the multiplication. There are still some works that you need to do here. You have to check whether it satisfies all the group axioms, all the 4 group properties. But I'll not prove it here. But I'll just introduce it because this is a very good example of non-commutative group, and we call it the general linear group, or we call it the matrix group. And we usually write it as GL2N. So GL stands for general linear, and then 2 stands for the dimension. So actually, GL2Q. Yeah, GL2Q. So Q is the elements here, the individual elements inside the matrix. So this is a very popular group. There have been a lot of applications for general linear group. So when you do like 3D animation, when you want to do like rotation and so on, there is another set of group which is called a special group or something, SO2, SO3. So they have they give this kind of group a name because it's very important. It has a practical usage of it. But for here, I just introduce it because it's a very good non-commutative group example. So when we have something that is non-commutative, then okay. So suppose so from here we can see that group not necessarily needs to be commutative. But if in the case that the group is commutative, like for example integer, where we have a plus b is equals to b plus a. So if you write it as a property, then we say that pick any 2 elements, a, b from the group, and then a slash b is equals to b slash a. Then we call this a commutative group, or we also call this an abelian group. Abelian is the name of a mathematician. So abelian group is basically a group that satisfies this additional property called commutativity. So here we can look at the small pictures of how it looks like. So a group, in order to be a group, you have to satisfy all these 4 properties. In order to be an abelian group, you have to satisfy this additional property, commutativity. So so far, any questions? I think we should take a quick break here. Maybe we take like a 2 minutes break, 2 to 3 minutes break. So if you have any questions, you can also ask now. Then we will continue in a bit. Seems like this whole sharing needs to take up to 4 hours and not 2.5 hours. Okay, so we come back at 10:11. Okay. Yeah. Okay. So let's continue. I guess today, let's target to like finish the group part of this whole thing. Yeah. Okay. And then sorry for like taking so long. I guess. Uh. Okay. Let's do the part behind quickly. Okay. So we have talked about groups, right? And just now, like I mentioned, uh the groups that we generally show are infinite in size, infinite in size. So like for example, the integer, there are infinite number of elements in the integer. And then, so there are also some examples. So for example, for this one, for the group of just -1 and 1. So the size is finite and there are only two elements inside. And there's also this very special group, which is called the zero group. So you can check that. So for this group itself, right, the inverse is itself, right? So 0 multiplied with 0 is 0. And then you can only do this for yourself. So close is automatically closed. And then associativity, everything is automatically satisfied in this group. So this is a very special group and it only contains one element. So we give the size of a group a name. We call this the order of the group. So a more fancy way to write this down is that if we have a set, if a group G, which is S and the slash, then we call the order of the group. We use the symbol, the two straight line symbol to call the order of the group. So this is basically just a fancier name for the size of the group. So now the question is, okay, I have group of size 1 and size 2. So can I have group of arbitrary size? So let's say I want a group of size 10. Can I have this group? That okay, so since we want a group of size 10, so then how do we even construct such a group? It seems not a very easy question. So like for example, if you can see that I have done a lot of things, right? And then you can't just like simply do stuff. Okay, maybe I just do like 1 and then 2 and so on until 10. This is a group, this is a set of size 10. And then if you define addition on it, the problem is that it's not closed because 10 plus 1 is 11. Then 11 is not inside this set already. So it's not closed. So what can we do about it? Like, so it seems not easy. And perhaps if you all have been doing a little bit of cryptography, you might know about modular operations. So modular operations is very helpful in a way that it seems to be able to solve the problem of having of us trying to construct a group of any size. Okay, so now let's check whether is this a group or not. Is that and then remember this notation. So this notation means that I just put any two elements here and then I do modulo 5, modulo 6. So for those who don't know what is modulo 6, so modulo 6 basically means that remainder after divide 6. So like for example, if 3 plus 3 is equal to 6, 6 mod 6 will be equal to 0. And then this will be 7. 7 divided by 6, we get the remainder 1. More formally, if you want to do this, you can take something like 7, 6, and then this is 1, this is 6, and then this is 1, and then the remainder is here. So that's how you get the modular operation. So now I would like to make a poll and ask whether is this a group or not. Okay. 2 votes are saying that it is a group. So remember that if you want to check whether something is a group, you have to check that whether it satisfies all the 4 properties. So I'll give it another 10 seconds. Okay, so we have 6 votes saying that it is a group and 3 votes saying that it is not a group. Okay, so now let's try and see whether it satisfies all the 4 properties. Let's try and prove it. Get our hands dirty. So do we have an identity? Yes, we have, right? We can always set the identity to be 0. So okay, we can set this identity to be 0, right? So we have that we have 0 plus 3. If we do this mod 6, then we get 3, right? So we get back the same element. Now let's look at this scenario. Okay, so we have 12, right? So 12 plus 6 modulo 6 is equal to 0. Why? Because 12 divides 6, right? So this will mean that 12 slash e will become 0. So the 0 here is e. So this will mean that 12 is equal to e. But does it make sense? Because this is okay, if we are taking it from counting theory, right? This is actually saying that 12 things is equals to 0 things. So 12 banana is equals to 0 banana. So then our identity property is not satisfied already. How can 12 be equals to 0? Even if I put e is equals to 0, how can this be true? So this is actually not a group. So there seems to be okay, so although it is not a group, right? It seems to still be a very good candidate for us to construct a group of the same size. But how do we even so we want to say that 12 is equal to 0. So how do we even do that? So for that, we have to redefine our modulo operations. So we say that for an integer a, b, and n, we say that a is congruent to b modulo n if there exists an integer k such that a minus b is equals to kn. So this is just a fancy way of saying that b is a remainder of a. So like for example, this is just saying that a, and then you divide by n, this is k, and then this will be kn, and a minus a kn will be b. I think this will be negative b actually. But okay, never mind. So basically saying that a is the remainder of after a divided by n, this will be remainder of the remainder will be b. But note that k here could be not a positive number. This could be a negative number as well. So so we use this notation to say that a is congruent to b modulo n if this satisfied. So this is another way of saying like equality, right? So so we redefine our definition of equality to force it to become a group. So under this definition, right, 12 is equals to 0. Because so under this definition, we can say that 12 is congruent to 0 modulo 6. So this makes sense. 12 is equals to 0. This doesn't make sense. This doesn't make sense. 12 is congruent to 0 mod 6. This makes sense. So if we want to make the previous things that we have defined just now to become a group, we have to redefine our equality. Because we cannot say that 12 is equal to 0. We have to redefine it to be 12 is congruent to 0. Or we say that congruent is just another way of saying equivalent. So we redefine our definition of equality to force it to become a group. But we have to check whether our new definition of equality is well defined or not. So the most easiest question that we will ask that if I say that 12 is equals to 12 is congruent to 0, right? And then this I say that 0 is congruent to 6. So does that mean that 12 is congruent to 6? So I can always define any sort of equality. I can say that monkey is equals to a dog, dog is equals to a cat. But this should always guarantee that monkeys is equals to a cat. So this property, we call it transitivity. So if we want our equality to be well defined, we have to satisfy transitivity. Otherwise, it doesn't make sense. So other than this, we have to also check whether something is equals to itself. Does monkey is equals to a monkey? So can we say that? So is 12 congruent to 12 modulo 6? So is this true or not? And then if I say that 12 is congruent to 0 modulo 6, does it mean that 0 is congruent to 12 modulo 6? So given that a monkey is equals to a dog, does dog equals to a monkey? So, okay, it seems very obvious, right? Okay. At first, it seems very obvious, but we call this property that something is equal to itself, call it reflexivity. And we call that the things that is, we call this property that given A is congruent to B, B is congruent to A, we call this symmetry. So now I would like to say a theorem. So a theorem says that if our equality relation satisfy all these three properties, which is the following three. So the first one is A is equals to B, B is equals to C. This would imply that A is equals to C, and A should always equals to itself. And I should always be able to sort the elements, and they will also be equals to each other. Then this will be well defined. Okay, so you might say, okay, this is very obvious. Don't talk nonsense to me. But suppose, right, if we redefine our equal to be something like this. So if we say that A is congruent to B if their difference is 1. So like, for example, I will say that 1 is congruent to 2, right? Because 1, if you put 1 here, you put 2 here, and then 1 minus 2 is negative 1, and then it is in this range. And then obviously 2 will also be congruent to 3. And then the other way around also works, right? So 2 will also be congruent to 1, and then 3 will also be congruent to 2. And then if you check, like 1 will also be congruent to itself. So it will satisfy this property and this property. But 1 is congruent to 2, 2 is congruent to 3. We see that 1 is actually not congruent to 3. Why? Because if we put 1 here, if we put 1, if we put 3 minus 1, this is 2, right? 2 is larger, 2 is not inside this range. So it is not transitive. So it is not always obvious that when we define our equality, it is not always obvious that it will always satisfy all these three properties. And indeed, you have to check whether it satisfies all these three properties. So if it doesn't, right, then your equality doesn't, it's not well defined. Your equality does not make sense at all. Okay, so so far, any questions? Okay, then I'll move on first. Okay, so to recap a bit, we are trying to redefine equality because we want to fix the problem of 12 is equals to 0. So this is the problem we want to fix. So we are trying to redefine our equality. And for our equality to make sense, it has to satisfy all these three properties. And it is not always true that if we anyhow redefine our equality, these all three properties will be satisfied. But okay, so if our equality satisfy all these three, we call this an equivalence relation. So what is an equivalence relation? An equivalence relation is something that satisfies all these three properties. So now let's check whether modular operations satisfy them. So first, reflexivity. So suppose we say that A is congruent to A. Is this always true? So by our definition of modulo, so when we say that we say that A is congruent to B modulo n if there exists an integer k such that A minus B is equals to kn. So this is our definition of equality of congruent. So A minus A is 0, and we can always write this as 0 times n. So 0 k is an k can be any integer. So 0 is an integer. So reflexivity is satisfied. So by this, we are saying that any integer, maybe 13, 13 is also equal to 13. So symmetry, if A is congruent to B, we want to prove that B is congruent to A. So how can we prove that? So by definition again, we say that A is congruent to B if there exists an integer k such that A minus B is equals to kn. And then we multiply negative on both sides. So we multiply negative on both sides, then we get that B minus A is equals to negative k times n. And negative k is still an integer. So this would mean that B is congruent to A if A is congruent to B. So symmetry property is satisfied, reflexivity is satisfied. So last one, transitivity. Is this satisfied or not? So this is the hardest one to prove. So again, we have A is congruent to B. B is congruent to C. By definition, we have this, and then by definition, we got this. So by definition of A is congruent to B, we have that A minus B is equals to K1 times N. B congruent to C, by definition, B minus C is equals to K2 plus N times N. And then we add these two equations together. So we have 1 and 2, and then we add 1 and 2 together. Then we get that A minus C is equals to K1 plus K2 times N. And K1 plus K2 is still an integer because K1 is an integer, K2 is an integer. So we can conclude that A congruent C modulo is A congruent C modulo N. So transitivity is satisfied. So so we prove that modulo operations satisfy all these three, and modulo operation is an equivalence relation. And with that, we can come back to our original question: is this a group? So we have to redefine the equality to make it in the group. So we can't say that, we can't just put Z here in some sense, right? Because Z, in integer, right? Integer, you can't say that 12 is equal to 0. That doesn't make sense. But we redefine our equality, we have to say that this set is actually a set of integer, but with modulo equality for the to make sense of the group of properties. So it's kind of worthy to say this whole thing, and then we are trying to find if there are any way to simplify this notation. So and then when we have equality, right? So we say that 12 is equal to 0, and then we also have that 6 is equal to 0. Then let's say if we say that 12 is equal to 6 is equal to 0, so this is all hold true in the congruent world, in the equality world. Then if we put this thing as a one element, then how many distinct elements are there in this integer but with modulo equality? So we kind of it's kind of hard to do this sort of counting. So okay, until here, any questions? I'm scared that I talk too fast or it becomes a little bit too confusing. Do you all have any questions? Or is it good and I can continue? Okay, seems like some of you are saying that it's okay. Okay, so let me just continue and finish this part first. Okay, so now we see, okay, so this is a theorem. I will not prove this, but basically equivalence relation will partition a set. So we consider the modulo 4 case. We see that, okay, 0 is congruent to 4. 4 is also congruent to 8. 0 is also congruent to -4 and so on. And then if you look at the another scenario, which is the one with 1. So 1 is congruent to 5. 5 is also congruent to 9. The reason being that 1 divided by 5, divided by 4, the remainder is 1. 5 divided by 4, the remainder is also 1. So these are all congruent to each other, and so on. So everything here is equal. So everything in this set is equal to each other. Each of the set is equal to each other. So essentially, kind of it will partition the set into four different things. So originally we have -infinity to 0 to infinity. Now it is partitioned into 4 sets. So now I'm gonna do something that is kind of maybe not so intuitive. So I'm gonna label this set as one thing. So I call this 0 bar. And I call this 1 bar, 2 bar, and so on. So I put this whole set, I label it as one single element. I label this whole thing as I call it 0 bar, and I label this whole thing, I call this 1 bar. I label this whole thing, I call this 2 bar. So when you ask what is this element is a set. Okay, so this is a set. Okay, so with this itself, we can form this thing. Okay, so what is this? I just put all the 0 bar, 1 bar, 2 bar, 3 bar together here, and then this is a set of 4 sets. So this whole thing is a set, and then everything here is a collection of. So everything here is a collection of stuff. So this is a set of sets. So if you think about it in a box, so if this is a big box, then inside it contains 4 small 4 box, and then inside contain many elements. But yeah, so we have this, then we have addition. But how do we add these two boxes together? How do we do addition here? So we define an addition. We define addition on set as, if I do A plus B, then I will take all the elements in A and I take any elements in B and add them together. So essentially, essentially what I'm doing is that I take maybe like 0 here. So let's say if I'm doing like 0 plus 2, then what I'm doing is that I can do something like I just take any 0 element. So maybe this could be 4, and then 2, this could be 6, and then I add them together. This will be 10, and this 10 will be inside this set. So this, when I add these two set together, it will still become a set. But I define the addition of set as I just take any element here, I add with any element here. Okay, add with if this is 0 plus 1. So if I write it that way, right, it is then I call this Z4. Okay, I call this Z4. And then we can see that this is a better structure. And then this is also well defined. Why? Because 3 plus 3 will not be equals to something like 6. So this is actually equals to 2. There are no 6 here. 3 plus the set of 3 bar plus 3 bar is equals to 2 bar. Why? Because with our definition of the set addition, if you take any element from here, you add them, then you can get all the elements here. So I don't have to say that this is integer Z with modulo equality. I don't have to say this whole thing again. I just put this, I represent it as a set of sets, then I can have a better structure, and I can also easily count the number of elements here, which is 4 elements. And I don't have to, I just need to redefine my addition, which is my addition needs to work on sets. So yeah, so with that, then I finally can say that this is a group. Okay, yeah, so okay, so far. So then okay, so by having this amazing, actually not amazing, but somewhat confused construction, right? We have what we have done so far. Like we have partition, and then we do something like we put it into a box of box, and then inside the box have different elements, and then we define how to add these two boxes together. So we add these two boxes together. We basically take some element here, we combine some element here, and then we add it together. We become another box. So there's a lot of different things. There are a lot of things going on, but essentially what we actually finally able to do is we can create group size of whatever size that we want. So Z2 is the parity group and is defined on modulo 2. And then Z5 is modulo 5. It has a size of 5. So more explicitly writing it out, this is 0 bar, 1 bar, 2 bar, and then 3 bar, 4 bar, and 5 bar. There are no 5 bar. And then for any group size n, we can just do the integer group modulo n, and this will be size n. So now the interesting question is this a group? Okay, oh, wait, what's going on now? Wait. So I have been defining addition. Okay, I add these two collections together, then I get another collection. So this collection is defined by I take one thing here and take another thing here, and then I become here. So now I suddenly come up with multiplication. So what is this multiplication? So maybe I can also define my multiply by I take something here, and then I take something here, and then I try and multiply, and then I get something here. But okay, perhaps that's too much to say for now. So we just skip whether this is a group or not yet. But yeah, so that's on the topic on finite groups. Oh, yeah. Okay. So let me just quickly continue. So this is the last part. Okay. So before I end on the topics of group, I want to share one interesting property. So suppose we have a finite group of G and then with the operation slash, and then the order of the group is n. So remember, this is just a size. So now we take any element G. We want to show that, okay, so what we are claiming now is that there exists an element K such that when I do this, when I slash with itself K times, I'll get back the identity element E. So for example, in the case of this -1 and 1 group, I can, if I repeatedly do the operation on -1, then I will somehow get back the element 1. Obviously, this will also be the case for 1. And then for the group of Zn, right? So Zn, if I repeatedly add A for n times, right? I repeatedly add A for n times, then okay, my mouse is still okay. So if I repeatedly add A for n times, this will become NA, and then NA will modulo n will become 0. So you see that, okay, it seems that if I have a finite group, if I take any element and then I just repeat do the operation on the same element for some amount of times, I will get back the identity element. So how do we, why is this the case? So we try to prove this property. Okay, so suppose, okay, now let's just let G1 to be G. So G1 is just G applied to G the same one time. G2 is G applied to G 2 times, and G3 is, and so on, G many times. So okay, if you think about it from in terms of the elements inside the set, right? So now I have a big collection, and then now I have so this is a finite group. So inside we have a lot of elements. Okay, so suppose my first element is G1. So this is G1, and then because of the closure property, after I applying it to myself, I could get something here. So this could be G2. And then I apply the G to G2 again. So here I multiply with, not multiply, I apply the group operation with G. Then I get G2. Then maybe I apply again, I get G3, and this will be my another element, and so on. And then you realize that after a certain amount of times, you will cycle back to one element because you have only n elements here, right? So let's say this is the case, right? This is a group of size 9. So no matter how you jump, right? If I do this operation, okay, so if I have nine elements here, if I do this operation for 100 times, there must be a times where I have to jump back to an element that I have encountered before. So essentially forming a cycle. So what I'm saying now here is that, okay, I keep repeating applying G and I get n plus 1 elements. So, but then there are only n different elements. So this means that there must be at least a pair of distinct elements in the chain that are the same. So basically, it's the concept of repeating cycle. So like I jump from here to here, and then I jump from here to here, and then I jump again. Because I only have finite number of elements, like for example n, if I do this operation for 100 n times, then certainly I will jump back to an element that I have seen before. So I can have an I that is not equal to j, such that gi is equal to gj. So remember, this is just repeating g for I times, and this is repeat j for j times. So I have this property where I will jump back to a same element. Okay, so now suppose that, okay, we know that I is not equal to j, but suppose that I is larger than j. So now what we can do is that we can take the we can move all the g here. So we move all the g here. We basically just multiply the g inverse. We know that g must have an inverse. So we move all the g to the other side. Then we get that g I repeat, do g for I minus j times, I will get e. Right? Because I just multiply with not multiply, I just slash with g to the inverse on both sides, and then I repeat do for j times until one of them become empty. So when one of them become empty, it will become the identity element. So when this is the identity element, we have our we basically prove it already, because k, right? So K is we want to find something such that when we repeat doing the same operation on GK times, we get back the identity element K. So this I minus J times is exactly our K. And we found that when we repeat doing G for I minus J times, we get back the identity element E. Okay, but then now you might ask, okay, what is I and J concretely? So perhaps it's not that clear that maybe I and J is not that easy to find. But what we are doing now is we prove that there must exist a K, although we might not know what this K is, but there must exist a K such that when I apply this G for K times, I'll always get back the identity element E. So when you look at the group in terms of, if you know some other groups, like for example, modulo and then you do something like G to the power of K, something like that. But okay, so if you don't know, then it's fine. Then, but basically what I'm saying that is that if you repeat the same group operation on the same element for K times, then it will become the identity element E. So yeah, so this is the proof. Okay, so the takeaway from this is that from studying group theory is we prove for one thing, then this property will be applied for everything. So that property that we proved just now is applied, can be applied to any group. And then if we have an algorithm that solves the equation for one group, that algorithm will basically solve for every group. And if we have cryptography protocol for one group, perhaps we can do the same protocol for every different group. So this is something interesting to think about. And then there are many further topics. For example, quotient group. If you look about when you are trying to do cryptography research yourself, quotient group is basically something that you kind of want to divide a group with another group. And then there's also the notion of group homomorphism, which you map a group into another group. And then normal subgroup, simple group, soluble group. There are many different notions of this. But yeah, so basically that's all about group. Okay. So I have finished my sharing for today. Okay, so hopefully you all learn something. So next week we will talk about rings and we will talk about multiplication. So there will be new monkeys coming in. Okay, so before we end this meeting, any final questions? Sorry for taking 1 hour and 40 minutes. Okay, if you have any questions, maybe you can stay after you can stay after everyone leaves. But I guess if not, then we can probably end this already now. So we will continue the further part next week. I forgot to mention one thing is that towards the end, right, we will try and solve this equation. So we will remember at the very beginning we have this this CTF problem, right? So towards the very end, we will solve this problem, and then you can be the one of the 3 and 4 person that can solve the hard crypto challenge out there. So hopefully that you will still come next week. So see you all next time. Thanks. Yeah, if you have any questions, you can ask. Yeah, let's stop recording. Sion, what's your question?